Okay, so this is one of the typical voice signals that we have. Like as I'm talking right now, this is part of the signals that I'm transmitting to you. And below this one is a modulated signal. You can see it's a little bit more complicated, have some of the frequency changes and also some intensity change. And in the previous lecture, you heard about why you modulate a signal, and there's a frequency modulation, there's amplitude modulation, right? Why do you need to do that? Because when we are transmitting our signal, we want to modulate them and in a way that we can preserve our signal better, and later on we can decode these signals, and then we know we are not losing any information. That's all why we need to modulate them. We'll talk a little bit more and do a little bit exercise on that. So here is one of the examples. Like now we want to modulate a signal for transmission. And earlier you see you can do linear modulation. You can actually do all kinds of modulation. You can apply a parabolic function to your signal. You can apply for sinusoidal function. So this is basically your choice. So here I have an electrical device will be turned on by a parabolic input. So this is my input signal, t squared. If the carrier signal to be used for transmission is c of t 3 times cosine 2t, and this is our carrier signal. So we are applying this carrier signal to our input. Basically, when you're multiplying these two functions together. Graph the modulated signal that will activate the device. So basically, what you need to do is you first put in your parabolic signal. So we all know what a parabolic signal looks like. So we have a t, this is function, and then, so this is t squared signal, right? And then we also have this transmission signal, it's a cosine signal. And then once we apply these signals, so we actually applying cosine signal with the parabolic signal, so it will look like something like this. So let's see whether we did it correctly. Okay. So you have your original input signal, it's a t squared, and you apply your carrier signal and 3 times cosine 2t. And then this is how you ended up with and this blue signal. And then, so when we are transmitting our signal, once we modulate it, we're actually kind of giving another additional character to the signal we're transmitting. Right? And later on, actually, we need to receive this signal, and then we need to decode. We need to know what was the t squared that we put in. But I know what I put in, which is the cosine 2t, this function. So I just need to take this cosine 2t function out of this equation. Then I can restore my original signal. And once you do that, you need a certain filter to filter out the signals that you don't want. And there are 3 general type of filters: low pass, high pass, and band pass filter. So low pass, this is very intuitive. So low pass just means the low frequency signal will pass through, and high pass means the high frequency signal will pass through. And band pass, basically, you can pick the frequency you want, and you can reject both the low frequency and the high frequency signals as you want. So this is basically a very, very typical shape of a band pass filter, and the x-axis is the frequency. Okay, so we can take a look at this one. This is called the demodulation exercise. So for example, we are demodulated our signal. Now we are at the receiver side. We are receiving this signal, and we want to know what our original signal before the modulation looked like. And then here is x is our receiver, and we come in with this function because it's called m of t cosine omega t, so it was modulated. And then I put in another signal to help with my demodulation. So I give this receiver additional signal called cosine omega t again. Why am I doing this? You will know later on how I can remove this signal by doing this trick. So once I put in this additional cosine omega t signal, and my original signal my received signal become m of t cosine square omega t. So I can do a transform of this equation. We know the cosine square is equal to 1 plus cosine 2 of that angle, and 2 omega t divided by 2. So once I do this transformation, I have received a signal which is a half of mt, which is my signal I want to restore, plus a half of mt times cosine 2 omega t. Then I apply a low-pass filter to this equation. What it does is, okay, so first the receiver pick up the signal, and then I apply the signal. Okay, then I apply this low-pass filter. So which part of this equation has a lower frequency? M of t plus m of t times cosine 2 omega t. Which one has a lower frequency? So apparently the m of t has a lower frequency because cosine omega t 2 omega t is a fast oscillating cosine function, and it's oscillating at 2 times of the frequency than what I applied before. So see if you can put in some values of time, and you know this one oscillates twice as fast than cosine omega t. So as I'm applying my low-pass filter, meaning my low frequency is going through. So I take away the cosine 2 omega t part. That's how I ended up with a half of mt. This is my original signal that I want to restore. Okay, this is why you need to modulate a signal, and then you need to do the demodulation to restore your original signal.